K-class classification. This is a type of supervised learning where the goal is to categorize instances into one of K different classes. That is, we may have multiple classes like C1, C2, C3 up to CK. Whenever you get any input, let's say X, what is your aim? You want to put this into the right class. It may be C1, C2, C3 or any class up to CK. In order to do this, you will need a discriminant function similar to the way you dealt in case of two-class classification, and we'll see what modifications are to be made so as to accommodate K classes instead of just two. Before we get into the main discriminant function, which will accommodate all the K classes, we'll also go through certain methods which are directly intuitive from the two-class classification that we've learned. And you should be thinking like, why can't I use this method? Because this is way simpler and directly intuitive from whatever you learned in two-class classification. And we'll also see why these methods are not the best methods, or the discriminative function that we do for K-class classification seems to be an even better method than these ones. Okay, so it's not that you can't use this, you can use whichever method you feel like, but we'll see through the methods and see the positives and negatives. We'll also see the final one in which we have a K-class discriminative function. The first one is a one versus rest approach. First one is a one versus rest approach. So in one versus rest approach, what happens is we've already learned a two-class classifier, that is a binary classifier. Here what you do is you train K different classifiers, K different two-class classifiers, and what does each of those classifier do? It learns to distinguish between a specific class and all other classes. That is, it would say whether it belongs to CK or not CK. It does not differentiate between each class. Instead, every single classifier is trained to identify whether it belongs to one class CK or not. So you have K such different classifiers. That is, for C1 you have a classifier which would say C1 or not C1. Then you have another classifier for C2 which would say C2 or not C2. Then you have another classifier which would say C3 or not C3, so on up to all the K. So if all the other classifiers says it is not in that class, and one particular classifier, let's say C2's classifier, says this is in that class, this means the particular input X is in class C2. But there may be cases in which multiple classifiers may tell you that this belongs to my class. In such cases, what you'll have to do, you will have to use a confidence score. The confidence score will help you to predict the right class. So this is a very simple and intuitive method, but the only problem is when the classes are imbalanced, it may not work well. That is, let us say you have many classes C1, C2, C3, etc. Let's say C4, C5, but there may be a case where your data may be mostly composed of C1 and C2, and there are very less data belonging to C3, C4 and C5. In such cases, your model for C1 and C2 would be very well trained, but the same won't be the case with all other models. So you won't have all the K models which are having equal efficiency. So that's a concern in this method. One more issue is, there may be a case where you have a lot of ambiguous scenarios. That is, let us say you have this particular boundary, the decision boundary obtained from one particular model, which says above this line it is C1, line in the sense decision boundary, and below this it is not C1. Okay, and you have another decision boundary, this one, which says above this it is C2 and below this it is not C2. This is what the decision boundary 1 and decision boundary 2 says. These decision boundaries, they actually divide the whole area into 4 regions. There is R1, R2, R2, R3 and R4. There are 4 regions. Take the case of R1. What is the scenario in R1? According to the first decision boundary, that is this one, according to the first decision boundary, it belongs to C1. And according to the second decision boundary, it does not belong to C2, right? It is in the lower end of this decision boundary, which means it does not belong to C2. So in case of R1, it is very clear. It belongs to C1 and not belongs to C2, which means it is the region where class is C1. Very clear. What about the region R2? Here, according to the second decision boundary, it belongs to class C2, right? Belongs to class C2. And according to the first decision boundary, it belongs to not C1. So it belongs to C2 and not C1. So fair. This is of class C2. What about the region R3? Think about R3. Here, according to the first decision boundary, it is not C1. And according to the second decision boundary, it's not C2, which means it's not in either of the classes. And let us say we are considering that there are some areas which do not belong to class C1 or C2. So in that case, okay, R3 is also fair. What about R4? According to the first decision boundary, it belongs to C1, right? And according to the second decision boundary, it belongs to C2. So both the decision boundaries are saying it belongs to my class. So R4, according to first decision boundary, is in C1 and according to the second is in C2. So this one is an ambiguous area. We are not sure which class to assign to. So these sort of ambiguous areas may come up in case of one versus rest classifier. So it is a drawback in case of one versus rest classifier. The next one, the next classifier we'll use in order to do K-class classification is again directly derived from two-class classification, and it is called a one versus one classifier. Our second approach is a one versus one classifier. What is a one versus one classifier? Contrary to the way we dealt with in the previous one versus rest classifier, in one versus one, we have not just K classifiers, but K into K minus 1 by 2 classifiers. That's what we have. And what does each classifier do here? Each classifier distinguishes between any two classes. That is, there will be one classifier which would distinguish between, let's say, C1 and C2. Maybe one would distinguish between C2 and C3, so on. So, for example, if there are 5 classes, let us say C1, C2, C3, C4 and C5. There are 5 classes. In this case, there will be one classifier which would identify C1 and C2. So this classifier would say whether the point belongs to C1 or to C2. Among the two classes, which one does it belong to? The second classifier, it would say whether it belongs to, let's say, C1 and C3. Third classifier would say C1 and C4. Fourth one, C1 and C5. That is, among C1 and C5, which class does our input point belong to? This is what this classifier would decide. Similarly, that is, we want all the combinations. With C1, we took all the combinations. Now with C2, we'll have C2 and C3, then C2 and C4, and C2 and C5. With C3, you have again C3 and C4, C3 and C5. So on, we'll have a lot of classifiers. How do you count the total number of classifiers required in this case? And one more thing, each of the classifier will tell you which class does it belongs to according to the two classes that particular classifier is trained for. So how do you finally decide which class among the K classes does it belong to? Each of your classifiers, they will vote for one among the two classes. So this will vote for C1 or C2, any of those. This will vote for C1 or C3. This will vote for C1 or C4. So among the classes it is trained to, that classifier will vote for one among the two classes. At the end, you will count all the votes, and finally whichever class gets the maximum number of votes, that will be chosen as the class among K classes. This is the idea. So in this case, how many classifiers do you need? Let us just count. That is, how does K into K minus 1 by 2 come up? That's what we are going to see. So let us say you have a total of 10 classes. Okay, 10 classes. In that case, the first class you will have to compare with all the remaining 9 classes using 9 classifiers. So you have a total of 9 classifiers now, okay? Plus the second class you have to compare with all the remaining 8 classes, because you already compare with first class when you were considering first class. So for the second class you have to still compare with the remaining 8 classes, so 8 remaining. Plus for the third class you have to still compare with the remaining 7 classes, 7 plus dot 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 plus finally till you reach 1. So this is the sum of first k minus 1 natural numbers. That is, if k is the number of total number of classes that you have, then the number of models you need is the sum of k minus 1 first k minus 1 natural numbers. What is the sum of first n natural numbers? It is n into n plus 1 by 2. So what is the sum of first k minus 1 natural numbers? It will be k minus 1 into k by 2. So that is this figure, k into k minus 1 by 2. Okay. So the problem with this method, 1 versus 1 classifier, is that this is computationally expensive. Why is it expensive? Because you have a large number of classifiers and you have to do a voting among them. So building that many number of classifiers and having all of them to make the decision, this will take up a lot of computation. And same ambiguous region problem that we saw in the previous classifier, that can occur here as well. How can it occur? Let us say there is this decision boundary which says whether it is class C1 or class C2, let us say. Then maybe you have this decision boundary which says it is class C3 or class C2. Similarly, you may have this decision boundary which would say class C1 or class C3. So here if you see this area, this seems to be in class C3. This may be class C2. This may be in class C1. But what about this area? This area, it belongs to C1, C2, C3. Which one? So this is an ambiguous area. In this area, you are not sure what to say. Which class should you provide? So this sort of ambiguous area occurs in 1 versus 1 classifier as well. So with both the classifiers 1 versus 1 and 1 versus rest, we had seen one issue is ambiguous areas. We don't know exactly which class to assign to. Such areas may occur. That is first problem. And the second problem is that computation, especially in 1 versus 1 classifier, because you want to make k into k minus 1 by 2 different classifiers, it is computationally expensive. We'll get into the next method, which is our main method in which we'll have a discriminant function. This is the method using which you can avoid all these problems. You won't have any ambiguous areas. You will directly reach the solution where you know this exactly is the class to assign. So this time, previously in 2-class classification, if you remember, you had a discriminant function. What was it that you used? You used something like y of x is equal to w transpose x plus w0. You used a discriminant function of this kind. Okay. So similar to this time we'll have k different discriminant functions. That is the modification we'll do in order to do k class classification. You will have k different discriminant functions. So you will call them as yk of x equal to wk transpose x plus wk0. Okay. This is how you will call them. So in this point where it is k, it can take any value from 1 to k. Okay. This is what the discriminant function will look like. So there will be k different discriminant functions. First one will be y1 of x is equal to w1 transpose x plus w10. The second discriminant function would be y2 of x is equal to w2 transpose x plus w20. Third discriminant function would be w3 of x is equal to w3 transpose x plus w30 and so on. So what this time the technique that we use is each of these discriminant functions, they will correspond to the class numbered by them. That is, this one will correspond to class 1, this is for class 2, this is for class 3 and so on. So whichever discriminant function has the highest value, that is the class you will choose as the class for this particular data point. So let us say you have a data point x. You substitute that x in this equation and you do it for y1, y2, y3. Also, you'll see the value of y1 of x, y2 of x, y3 of x, and so on, right? Up to yk of x. Up to yk of x, you will find the values of all these. Then, which among these is having the highest value, that is the class to which you will assign this data point. Let us say y3 of x has the largest value. Then the class is C3. This is how you determine in case of K discriminants, K class classification. So this is the condition here, that it is belonging to CK, that is class K, CK, if what is the condition? Yk of x, the yk of x should be greater than yj of x for all j not equal to k. Okay, j not equal to k. That is, there are k different classes. For each of those, you would say whether yk of x greater than yj of x. So this in short means you compare all the values of y's, whichever has the largest value, that is what you choose, right? There should be no other j among all these k values for which yj of x is larger than yk. That is the condition to choose yk of x as the largest one, and then k is the class you will assign to. Okay. So there is one question remaining. How do you determine the decision boundary between any two classes? So let us say you have two classes, CK and CJ. How would you say this is the decision boundary between CK and CJ, or C1 and C2? Take any two classes in this model. There are K classes. If you take any two classes, you should be able to say this is the decision boundary that is between these two classes. So how is it possible to calculate that? It goes like this. If there is a decision boundary between two classes, then it would be that, let us say two classes K and J, then yk of x would be equal to yj of x in that decision boundary, right? Because at that point, because it is a decision boundary, the point is not in J, not in K, it's right in between. So it is the decision boundary. The yk of x should be equal to yj of x. If this happens, what is yk of x? Wk transpose into x, right? Plus wk0. This should be equal to wj transpose into x plus wj0, right? wj0. This should satisfy in order to have a decision boundary. So this, if you take this term to this side and take x as common, and also you take this term to this side, then what will it become? It will become wk minus wj whole transpose x plus wk0 minus wj0. This is what it becomes. This is equal to 0. So this is the equation of the line. So when I say line, I'm considering it is in a two-dimensional space. If it is in a d-dimensional space, then this is the equation of a d-1 dimensional hyperplane. If it is a two-dimensional space, then this will be the equation of a line. This equation should give you the decision boundary between classes K and J. That is wk minus wj whole transpose x plus wk0 minus wj0 equal to 0. This should be the line of the decision. This is the equation of the decision boundary. Let us see what advantages do we have when you have decision regions using this method than the previous. Here, your decision regions of this sort of a discriminant function, it's always singly connected and convex. Let us understand what is singly connected and what is convex. Singly connected means it is single unbroken area, that is doesn't have separate disconnected parts. Let us say it would look something like this. I'm just drawing a sample decision boundary. So let us say this is my decision Ri, decision region Ri. This is decision region Rj. This is decision region Rk. Okay. Here if you see, the speciality is any decision region, let us say Ri, it doesn't have separate disconnected parts. It's a single part which has the whole region Ri. Moreover, this whole decision regions Ri, Rj, Rk, it is a single unbroken area. If you see Ri, it is an unbroken area, this particular region. Rj, it is unbroken area. It doesn't have different disconnected parts. That is with any particular region that is formed from the discriminant function that we used. Second thing is, there will be no gaps or breaks in the region. If you see this region, there will be no gaps, no breaks. Every point in the region would belong to the same class. For example, any point in this region Rj would belong to class Cj. Any point in this region Rk will belong to class Ck. Similarly, any point in this region Ri will belong to class Ci. So these are the specialities that you will have when you use this approach. And one more point we said is that it will be convex. What is convex? Convex means for any 2 points within the region, the line segment connecting those 2 points lies entirely within the region. That is, if you have 2 points, let's say a point here and a point here, then if you draw a line segment connecting 2 points in the region, let's say you drew this line segment, then every single point inside this line segment will surely lie inside the region Rk, right? This is the speciality of a convex. This is what you call as convex region. Okay, we can prove this. That is why for any 2 points in a convex region, let us say you take 2 points from Ri, maybe this and this. If you draw a line, all the points in that line would lie inside Ri only. How can you prove that? For example, if you take any 2 points, let us say your points in Rk. One is a point xa, let us say this point, and this point is, let's say, xb. These are the 2 points that you have. Okay. So let us say x cap is any point in the line connecting xa and xb. So x cap is any point in this. It can be anywhere. Okay. Anywhere in this line. If this is x cap, then x cap can be written as lambda into xa plus 1 minus lambda into xb, where lambda is a value between 0 and 1, 0 less than or equal to lambda less than or equal to 1. This is the condition. Then lambda into xa plus 1 minus lambda into xb. This will give you the value of x cap. Then you know that there is a discriminant function which is linear. The y of x that you told. Let me draw this on bit on that side. I'll draw the same area here, and this is my Rk. Okay, this is my point xa, this is my point xb, and this is the line. So x cap is somewhere in that line. Okay, and what is my discriminant function? Previously I had written the discriminant function, which should be yk of x is equal to wk transpose into x plus wk0. This is the discriminant function. Okay, if this is my discriminant function, then instead of, because the function is linear, what can I do? Instead of x in this equation, I can use y of x. So it can be yk of x cap is equal to lambda into yk of xa plus 1 minus lambda into yk of xb, right? It can be written like this. Now, xa and xb, both of those lie inside Rk. You know that from this here, that is here, both xa and xb, both of them lie inside Rk. What does that mean? By extension, that means yk of xa would be greater than yj of xa for any j, correct? This is the condition by which it should be in class K. You take the discriminant function, the K, the discriminant, that is the one which says it belongs to class Ck, it should be greater than all the other discriminants yj of xa. So, and similarly same with xb also, yk of xb should be greater than yj of xb, right? Greater than yj of xb for all j's. These two conditions are exactly satisfied. So if these two are satisfied, then yk of x cap would be greater than yj of x cap. This would be greater than yj of x cap for all j. Yk of x cap is greater than yj of x cap for all j. So from this, what can you conclude? If yk of x cap is greater than yj of x cap for all k, that means x cap also lies in the kth region. That is, x cap also belongs to class Ck. So this is the proof for convex property. So if you use this discriminant function method, if you have k different discriminant functions, and then according to the largest value of discriminant function, if you decide you have to allocate to which class, in that case, then you will have singly connected and convex regions. That is, you will be crystal clear of which class you should assign to. This is the advantage.